Hello everyone and welcome to this ninth lecture in the course of solar photovoltaic system design. And today we are beginning with a new section of study in this course where we will be talking about the fundamentals of solar cells and photodiodes. So we start with building upon some very fundamental principles of solar cell, touching upon some physics of their operation, and then we'll build upon it. We'll look at some of the ideal or the standard ways in which you can design a highly efficient solar cell. So we'll look at the solar cell design going a few lectures ahead, and then later on we'll go to solar PV panels, modules, the entire plant and other details. So in the previous section we looked at just the solar radiation resource assessment, and now we are entering into the technology of the solar PV plant, starting with the solar cell. So to begin with, let's look at one very fundamental definition of solar cell. We can say that a solar cell is an electronic device which directly converts sunlight into electricity. So if you recall, in our first lecture of this course, we talked about how solar PV is a very elegant technology, and that is, the interesting thing about its elegance is that this device converts directly sunlight into electricity. So that is very important, direct one stage conversion. And also, as you must have definitely observed, that this particular conversion happens without any moving parts, without any rotating parts, without any noise, without any emissions. So that's a very unique and interesting thing, special thing about solar PV, and that is what makes it, we can say, a simple and elegant power conversion technology. Just a single stage conversion and without any moving parts, noise or pollutants or emission. Now how does it happen? How does this magic, so-called magic, happen, that solar cell, just a flat surface and light hitting on it, and that is producing electricity? So let's see. So light shining on the solar cell produces both a current and a voltage to generate electric power. So as all of you must definitely be aware of, that when we talk about electrical power, we understand power is the product of voltage and current. So if it were to produce just a voltage and no current, not useful. If it were to produce only current and no voltage, again not useful. But solar cell produces both voltage and current, and the overall power is the product of these two. However, as we will look at it in the upcoming slides and discussions, that primarily, though it is producing both current and voltage, but if I want to model the solar cell, if I want to look at the electrical equivalent of solar cell, I model it as a current source. Okay. Why we do that? We will be talking about that in the lectures going ahead. So it's basically a current source, and as you understand, a current source also has some finite amount of voltage across it. So there is a current which is coming out, and there is a voltage which is across the terminals of the current source, and the power which is being produced is nothing but the product of that voltage and current. So if I just look at the very fundamental basics of this process, what is happening? So this process requires, firstly, a material in which the absorption of light raises an electron to a higher energy state, and secondly, the movement of this higher energy electron from the solar cell into an external circuit. And this particular thing happens usually through the interesting devices known as the semiconductors. So nearly all photovoltaic energy conversion uses semiconductor materials in the form of a PN junction. So as all of you must be aware of, if we look at the classification of materials in terms of their electrical behavior, there are these three classes. So one is the conductors, which usually the metallic elements, they are conductors, they conduct electricity very easily and in a very nice fashion. On the other hand, you have insulators, which do not conduct electricity at all, they are acting as the insulation. Whereas in between, there is this space where you have the semiconductors. So these are the very interesting devices which we will be talking about and which are used as the standard devices for your solar cells. So the semiconductors have this interesting structure where if you look at their energy states in which their electrons are present, so there is something known as the valence band in the semiconductor crystal where the electrons are present. So you have the electrons sitting in the valence band, and then there is a conduction band which is a higher energy state. Now under normal conditions with no light incident on them, just idle semiconductor sitting like that, now these electrons which are there in the valence band, they are all bound up with chemical bonds, they are not really free to conduct electricity. However, the interesting thing is that when a photon of light hits one of these electrons, this photon of light which is carrying some energy of the photon, let us say we call it as h nu. So, this energy when it is transferred to the photon, and if the energy is sufficient to cover this energy gap Eg, we call this energy gap as the band gap, that is the standard term used for this. So, if there is sufficient energy in the photon, so if your EPH or the energy of the photon is greater than or equal to the band gap energy, then this transition happens, that your electron jumps to the conduction band. And once it comes to the conduction band, now it is available, it is free to conduct electricity. So, that is the fundamental concept what is happening in a semiconductor. And though it might sound like, or for a novice person who is not aware of the technology, if they just look at a flat plate, light falling on it producing electricity, it might seem to a novice person like a magic, but actually there is nothing of magic here. This is how the structure of the semiconductor materials is, and due to which they are able to achieve this particular phenomena. So, whenever there is a photon of light hitting this semiconductor material and having the energy more than the band gap energy, the electron jumps to the conduction band, and there it is available to conduct the electricity. So, that is the basic phenomena. And then here, so first is that, as it says here, absorption of light raises the electron to a higher energy state, and secondly the movement of the higher energy electron from the solar cell into the external circuit. So, just jumping to the higher state will not suffice, because as we understand, for power output to happen, current has to flow. So, this should be connected across some load in the electrical and the external circuit. So, once the circuit is complete, now the electron has a path to go through, or the current goes in the opposite direction. So, as we understand, the current direction is opposite of the movement of the electron. So, that is how the fundamental concept of semiconductor and solar cell works. Now, as we said here, there is something of known as the PN junction. So, that is very important, in fact all the magic of a solar cell happens somewhere around this PN junction. So, we need to understand little bit on what is this PN junction. So, if you look at some of the semiconductor materials, the most popular and the most common one is silicon. Now, silicon, as you understand, comes in the fourth group, in the fourth column of the periodic table, and it has got 4 electrons in the valence band. However, silicon is very stable, and all these 4 electrons are bound up in different bonds with adjoining silicon atoms. So, this silicon atom which has got 4 electrons, this has got bonds with the adjoining silicon atoms in the crystal structure. So, every silicon atom has 4 electrons in the valence band, and it is bounded to adjoining 4 silicon atoms with these chemical bonds. So, all these electrons are engaged, no one is free to conduct electricity. So, it is like a very stable crystal structure, and then it continues like that, it is a ideal crystal is infinite, but there is nothing like infinite, but then conceptually we understand that ideal would be infinite like that, going ahead in all directions. So, it is a very stable crystal structure, but the problem is that there are no free electrons available, the charge carriers are all bound up in different bonds. So, if I want to increase the conductivity of silicon and make it more conducive for solar cell operation or any type of conducting behavior, I need to dope it with some particular type of elements. So, those elements, they produce some extra charge carriers. So, one option is that I can dope silicon with some element from the third group of the periodic table. So, there can be some element like boron or aluminium, which have got only 3 electrons in the valence band. So, now as you can appreciate, now instead of silicon, if a boron atom comes and sits here, that has got only 3 electrons in the valence band. So, let us say one electron will be bound here in a one bond, another here, third one here. Now, here interesting thing happens, that there is this vacancy, there is no electron there. Now, this vacant position can be called as like a positive charge. Absence of electron, electron is negatively charged, so we call that as a equivalent of a positive charge, or we call that as a hole. So these holes can act like excess charge carriers. So when you have excess holes, now holes are nothing but vacancies of where the electrons are not present, but because electron is negatively charged, the hole is relatively positively charged. So with this extra positive charge, so called positive charge, which we understand is not actually a physical charge but just the absence of an electron. So with this extra so called positive charge, we call this as a p-type semiconductor. That is what is shown here, So you have this blue one is a p-type semiconductor, and as you can see, this has got excess holes, those blue dots which are spread across that material. So if I dope it with a third group element like boron or aluminium, I create a p-type semiconductor. On the other hand, you have the fifth group elements, like common example is phosphorus, which has got 5 electrons in the valence band. So now instead of boron, let us say I put a phosphorus atom here, what happens? It has got 5 electrons. So the hole is gone, it is no more there. We have 4 electrons which are bound by the adjoining silicon atoms, and then there is one excess electron roaming around freely. So this again, if I dope it with fifth group element like phosphorus, there is, for every atom which I dope, there is one excess electron I am getting, and because electrons are negatively charged, so there is an excess negative charge, and we call this as a n-type semiconductor, shown here in pink color. So these n-type semiconductors have excess electrons. So those extra pink colored balls which are floating around in this pink material, that is the excess electrons, and we have the n-type semiconductor. So that is how we create, we do doping and we create p-type and n-type semiconductors. Now while each of these have excess carriers, but still it is not good enough for the solar cell. So we need to put them together and create a what we call as the p-n junction. So as you can see here in this graphical representation, we have p-type and n-type materials placed together with cross, side by side, there is a boundary between them. Now as you understand probably is that these are both silicon, so this is just silicon doped with boron, this is silicon doped with phosphorus, but it is essentially the same material. So when you are placing them together, obviously there will be a transfer of charge carriers across that boundary, because it is just the same material, just that one side has excess electrons, another side has vacancy of electrons. So what will happen, that with this natural phenomena of diffusion will happen when you put p-type and n-type semiconductors together. There is this natural diffusion of charge carriers which will happen across the boundary of p and n-type materials, and we get something like this. So when the materials are joined, carriers cross into the other region. However, the fixed ion cores that are left behind set up an electric field. So now this n-type which has got excess electrons, so electrons will move from the n-type to p-type, and alternatively we can say holes will move from p-type to n-type, though we understand that hole is not a physical entity, it is just the absence of an electron. So suffice to say that if we just take electrons, electrons are moving from n to p-type, and they will go to the p-type, and those vacancies which are there, which are the holes, they will go and sit in those vacancies. So basically the electron and hole pair will combine or neutralize each other, and this phenomena will continue till the time there is an equilibrium achieved at the junction. And once you have the equilibrium, a situation like this would arise, what is shown here in this second figure on the right. So there is something what we call as the depletion region. There is a depletion region, another name for this region also we call this as the space charge region. So this depletion region or space charge region gets formed, and this is the zone where there are no excess charge carriers. So basically the electrons from n-type have come and occupied the holes in the p-type semiconductor, and they have formed this depletion region or the space charge region. Now in this zone there are no excess charge carriers, but the interesting thing is, now what has happened is that the electrons or the negative charge has left the n-type, right. So whatever are the ion cores which are left behind in the n-type semiconductor, they are relatively positively charged, right. So this boundary of the depletion region on the n side, this is relatively positively charged due to this phenomena that negative charge has left that side. On the other hand, on the p side, initially the crystal was neutral, it did not have any charge. Now on the p side you have got excess electrons which have come. So this p side becomes relatively negatively charged. Okay. So that is always the polarity. So in a p-n junction the n side is relatively positively charged because it has lost its electrons, and the p type is relatively negatively charged because it has gained excess electrons. So this type of electric field sets up between the two types of semiconductors in a p-n junction. And the direction of the field, as it is shown here with this orange arrow, it is always from n type to p type. Okay, it is always like that. It is like a sort of, you can imagine like a capacitor type of thing with positive plate on the n side and negative plate on the p side. And this entire magic now would happen around this p-n junction. So this p-n junction is very, very crucial and important for the operation of the solar cell. Now moving ahead, let us look at some more fundamental concepts. So a good foundation for understanding the solar cell is the photodiode. So we will talk about this in today's lecture. What is this photodiode and what does it mean, how does it operate, and also how it relates to its very close sister diode, right. Diode, I think all of you must have studied in your fundamental physics also. So let us see a little bit more on the photodiode. A photodiode is, in the simplest case, is a p-n junction illuminated from the side. So this is what the photodiode looks like, just the same plain simple p-n junction. Okay. So as we just now discussed that your p type is relatively negatively charged and n type is relatively positively charged. So the signs are also shown here already, and the electric field is there from the n type to p type. So that is the p-n junction, by default it is there. Now interesting thing here, what is happening in a photodiode, it says here it is illuminated from the side. So in the physical photodiode, if you see what will happen, it will be like small cylindrical element but with a opening here. So there will be a sort of a glass opening on one side, a slit sort of thing for light to enter. So light is entering from the side, and as it is entering, as you can see here, this electron hole pair is getting generated due to light absorption, as we discussed in the previous slides, that if the photon energy is more than the band gap energy, the electron jumps to the conduction band and electron hole pair is getting generated. Now the magic is due to this electric field. So you have positive and negative polarity on two sides. Now this electron, as soon as it gets generated, it is sucked by the positive plate of this electric field. So electron is going to towards the n type, hole is moving towards the p type, the same electric field, it sucks the hole to the p type. So that is what is shown here. The blue one is the hole moving to the p type, the red one is the electron moving to the n type. And as we now already we are aware that n type already has excess electrons, right. So there are a lot of excess electrons in this particular side. So if one more excess electron comes, not an issue, and also it will not recombine because it is already the majority charge carrier on this side. And interestingly, on the other side also, as an excess hole comes, not an issue because this is again the majority charge carrier on this side. So it will also not recombine. And now what we would do is that, as I mentioned earlier, we will connect this with some external load here, the two ends of the photodiode. Electron will move out of the n type, go through the load and enter from the p type, or hole will alternatively move from p to n. So basically the current direction would be from p side to n side. Okay. So that is the operation of a photodiode. Now when we want to understand the photodiode in more detail, we talk about what we call as the IV curve. So as you can see here, a couple of axes, one is current axis usually on the y side and the voltage axis on the x axis. Now we will take a step back for a moment and help you recall something. Every one of you must have definitely studied in your school days of this good old Ohm's law, right. Ohm's law states that voltage is proportional to the current across a particular conductor. And also we can call the proportionality constant as the resistance. So voltage equal to IR, where R is the resistance. And this one, if I want to make the IV curve of this type of a device where voltage is proportional to current and V equal to IR, it will be just a straight line going like that from origin with the slope of the line, or in this case the reverse of the slope being R. So, this is true for basically the metals which are usually the conductors, and this type of devices they are known as ohmic devices. So, ohmic devices have this sort of behavior. However, not all materials are ohmic devices. So, semiconductors which we have been talking about in context of solar cells, they are known as non-ohmic devices. So, for a semiconductor this type of relationship does not hold true. It does not have a direct relationship between voltage and current, or not a linear relationship between voltage and current. It is non-linear. So, for semiconductor devices this IV curve is very important to understand how they are behaving, how their current and voltage across the semiconductor devices is interrelated. Now, this graph might look a little complicated at the first sight. There are 4 quadrants. First quadrant we are calling as the pass region. Second quadrant, it is the dark region here, there is a dark curve also nearby. Third quadrant we are calling that as photodiode operation, and fourth quadrant as the solar cell operation. Why we are doing that? We will look at it in a more systematic manner one by one. So, before we delve into this graph, let us look at a more simpler graph which is for a diode. So, this is the IV curve of a simple diode. Now, as all of us understand, you must have definitely studied about this. So, a diode always, it is used like a switch, and it operates or it conducts current only when it is forward biased. So, it is the same thing here, you have the current on the y axis, voltage on the x axis, and interesting graph if you see here, look at this IV curve of the diode in the first quadrant. The current through the diode is almost 0 till it reaches the threshold voltage, which is 0.7 volt for silicon and 0.3 volt for germanium. And once the threshold voltage is crossed, it is almost conducting linearly, the current is just going up, it is becoming like a conductor. So, for a diode, as we understand, we need to forward bias it, right. Now, what does this forward biasing mean? So, just to illustrate, so for a diode you have this p type and n type semiconductor, the 2 junctions, p n junction, and you forward bias or raise the potential of the p type. Why we are doing that? Just to relate it to what we studied just now for space charge region. So, if you have p type here and n type here, there is a space charge region in between. So, as we just now discussed, p is relatively at a negative potential, n is relatively at a higher potential or a positive potential. So, if I were to draw the the voltage characteristic across this junction, it would look something like this. So, n is at a relatively higher potential, this is the voltage across the junction, p is at a lower potential. Now, obviously when you have this type of a situation, it is not easy for a particular electron to cross this junction, there is a barrier or potential barrier we have created across the junction. So, that is why we do this forward biasing. So, with forward biasing what we are doing, as you can see, the p type is connected to the positive terminal of the battery and n type is connected to the negative terminal of the battery. So, what we are doing is that we are trying to erase this barrier and make it flat thing. If I am able to remove that barrier, then this diode starts conducting. So, that is the basic concept of forward biasing. Without forward biasing, that barrier or the potential barrier which is across the p-n junction, that does not allow the current to pass through, and that is why the diode is acting like a switch. So, whenever there is a potential barrier, it does not allow the current to pass through, you are in this portion of the IV curve. As soon as you cross the threshold voltage, you go in this region where it is acting like a conductor. So, that is the basic understanding for a diode. And then there is a concept of reverse bias also. So, if you reverse bias, then also there is almost close to 0, there is no current going there, until unless you reverse bias it so much that there is a breakdown happening, it will break down the barrier and the junction would be broken, and the device will not be useful anymore as a diode. So, that is the reason which definitely we want to avoid. Usually we operate it as a forward biased if I want to allow it to conduct, or if I want it not to conduct, then I put it as a reverse biased. Now, with that understanding, let us revisit this graph of 4 quadrant operation where we are talking about photodiode in more detail. So, in this context, let us look at a few things. As long as no light shines on the photodiode, it behaves like a normal PN junction with a reverse voltage, only a small reverse current flows, which is called the dark current. So, the topmost graph here, if you see where the dark curve is indicated, that is exactly the same graph like a diode, because photodiode also essentially is just a diode. Only difference between diode and photodiode is that in photodiode there is this possibility you create a slit on the PN junction, there is a possibility that incident light can come on the PN junction, create electron hole pairs and produce a photocurrent. If that is not happening, if your there is no light shining on the photodiode, then it is as good as a diode. So, that is what the topmost curve here indicates. It is similar, exactly similar to a diode curve. But the interesting thing happens when light is incident on the photodiode. So, as soon as light shines on the diode, a photocurrent that is independent of the voltage V is added to the diode characteristic curve. Because it flows in the reverse direction, it displaces the depicted IV curve downwards. So, as you can see here, as we increase the incident irradiation, the graph is shifting downwards. More irradiation means more photocurrent. So, from the first topmost graph we go to the second one. If we increase the irradiation, if we increase further, we go to the third graph or further down to the fourth graph, like that. And why we are calling it as the reverse direction? Because as we just now discussed, for a diode, this is P type and this is N type, and then we have the forward biasing. If I have forward biased a diode, then the current goes from P to N inside the device. However, if I look at it in this case, when I am having the photodiode operation, as we just now discussed also, that what is happening is that you have your N type and P type semiconductors, let us say, and the light is incident here and you are creating electron and a hole. Electron goes here, hole goes there, right. And in this case, if you see here, what will happen if I complete the circuit here, now the current goes out from the P terminal, whereas here the current was going inside the P terminal, right. So, if I am forward biasing the diode, I am calling that as the forward direction, current going inside the P terminal, and here when I am saying the reverse bias, then I am saying the reverse direction of current, photocurrent, the current is going out of the P terminal. So, that is why it says here that because it flows in the reverse direction, it displaces the depicted IV curve downwards. Okay. So, the sign convention here in this graph is that if there is an external source which is forward biasing the diode and pressing the current through the diode, that is the first quadrant operation, or the current is positive. But for a photodiode, as we just now discussed, the current will be coming out of the P terminal or in the reverse direction of the forward bias, and therefore we call that as the negative I, minus I. And so, for photodiode operation, the current is always in the reverse direction of that of the forward bias, and if I go on increasing the incident irradiation, then the amount of current also increases. So, that is how you see the graph is shifting more and more to the south or downwards as I increase the irradiation. So, this quadrant third operation is what we call as the photodiode operation. So, this basically here the first quadrant is mainly the diode operation in forward bias, whereas the third quadrant is what we call as the photodiode operation. So, photodiode operation and photodiodes, typical examples, they are used with applied reverse voltages as detector for optical data receivers. So, that can be like different applications can be there. That is one of the most popular or common application for a photodiode, is that when light is incident on the photodiode PN junction and the current is getting produced, and now as we have been understanding, the extent of current or the this photocurrent, what we call as the photocurrent intensity, will be directly proportional to the irradiation, how much radiation is falling. So, I can use this phenomena as a optical detector. So, if I can calibrate, I can just measure the current and tell how much radiation is incident on the photodiode. So, that is the common application for photodiodes. They are used in optical devices as sensors for light or detecting the light intensity. So, that is some fundamental understanding of photodiodes and diodes. In our next class, we will take this thing little further. We will look at one systematic comparison between diodes and photodiodes, and then we will go towards the electrical equivalent circuit of photodiodes. So, that is it for today. Hope to see you in the next lecture. Thank you.